Okay, so shall we start? Yeah. So my name is Pavlo Gavrylenko, and I'm going to teach two-dimensional conformal field theory. So if you have some questions, you can write to this email. So the lectures will be recorded and put on YouTube on the channel of Institute of Geometry and Physics. The lectures will be on Mondays from 11 to 13, and on Thursdays like now. So I want to ask, who are you? Most of you, are you physicists or mathematicians? Mm, mm. Ah, ah. Ah, okay. So, but mostly the science is kind of mathematical, sometimes not very rigorous, but I will also try to tell a little bit of physics. And by the way, did any of you study some quantum field theory or quantum mechanics? Mm. Ah. Mhm. Ah, something like this, but not a hardcore QFT with diagrams and so on. Ah, okay, I will tell some basic things about QFT, which basically allow to compute everything if you know only Gaussian integrals, basically. Mm. Oh, okay, so what all this will be about? So today CFT is a two-dimensional conformal field, a two-dimensional quantum field theory with conformal symmetry. It has many applications in different problems. For example, it is the theory which describes dynamic of the string worldsheet, because when people say so. When people talk about strings, they study the propagation of the strings in the space-time, and this since we have a one-dimensional object which moves somehow, it produces the trajectory, which is now not a world line as for a particle, but a worldsheet, and this is the explanation why it is a two-dimensional theory, because it's some two-dimensional object, and why it is conformal, because conformal symmetry in this case is part of reparametrizational symmetry of this worldsheet, in a sense that the only important data is the image of it in the space-time, and not the internal parametrization. So this is the explanation why it should be conformal field theory. And and there is another mm, application which looks completely unrelated. It's in the description of second order phase transitions. Mm. So in this case, the origin is different. So if we have some well, in two-dimensional statistical systems, well, classical statistical systems, like some Eisen model, for example. It's a theory with the spins plus minus placed in the nodes of a square or maybe even triangular lattice with the interaction equal to the product of these spins sigma x, sigma y over the neighbors. Like this product, this product, this product, all of them. And if we study the if we study the probability of some state described by the set of sigmas, probability given by e to the minus beta h bar, then we can compute some correlators like sigma of 0, 0 and sigma of mn. Correlator of such sigmas will be the sum of over all sigmas of the sigma times e to minus beta h of sigmas divided by sum. So it will be some function that depends on n and m. And if we take appropriate continuous limit of this system, then this function will behave like e to minus square root of m squared plus n squared divided by some psi, which depends on beta, divided by some power, plus corrections. So this is how the correlations in statistical systems look like, and there will be some critical point beta c, which can be which can be even computed analytically, such that this psi of beta c is infinity. So this is called correlation length. And so at this point, also other thermodynamic quantities have discontinuities, and if we go to this point, we lose this scale parameter in the system, and since scale is lost, the only option for the correlation functions is to be some powers of distance to some power plus corrections. And such situation is called second order phase transition. So in this situation, system becomes a scale invariant, but we will see later that in two-dimensional systems, scale invariants and conformal invariants are very, very close, and usually if you have one, then another one can appear. So and then this initial theory can be exactly solvable or non exactly solvable, but its behavior around this critical point will be described by conformal field theory. And also it turns out that this two-dimensional CFTs, at least some part of this two-dimensional CFTs can be classified, and in this way we can classify all maybe it's better to say to classify all such critical points maybe in some class. And so there is there is some subset of this conformal field theories which are called minimal models. And they are parameterized in general by two numbers, so they are called MPQ. But if we have some further restriction that the theory should be unitary, they are reduced to the case M, P, P plus 1. So and so as I will say at some moment later, they're described by a single quantity, which is called a central charge, and it has the following expression in this case, maybe in the general case. So the precise statement is that this fixed points or second order phase transitions are all classified for C less than 1. And in this case, we not only know this critical points, we also have a kind of full description. So independently on what our original theory was. So it's kind of universal behavior which is captured by 2D CFT. So, so it was some physical motivation to study this, but there are also purely mathematical motivations, because conformal group in 2 dimensions is infinite dimensional, and the same situation happens not only with conformal symmetry, with the space-time symmetry, but also other symmetries, like some Lie group symmetries, become coordinate dependent with homomorphic dependence on a coordinate, and it turns out that almost any such symmetry becomes infinite dimensional symmetry. So these CFTs produce a very big number of infinite dimensional algebras. And not only algebras, but also their representations. Like Versor, for example. It's the basic algebra which describes all the signs, and which should be present in any CFT. It has commutation relations like this. Kac-Moody. Or in other words, so I'm not writing the essential Kac-Moody part, so it can be also called a finely algebra. Oh. So it's a kind of usually algebra with a structure constant, say FABC, multiplied by the Laurent polynomials in Z, but also with the central extension. Oh, another algebra that appears here is the algebra of free fermions. Something like this. One of the variants of these free fermions for complex free fermions. Let us write it for real free fermions. So it is an anti-commutator. And there are also a lot of other algebras, but they become more complicated. So there are, for example, W algebras. And And basically, all the computations which are done in conformal field theory are some computations with such algebras and some operators acting between different representations. Mm. There are also other applications. For example, if you focus on a particular case of CFTs, which includes free fermions, then this case is related to integrable systems. Because, for example, KP hierarchy has a description in terms of free fermions. And actually, the general solution of it can be constructed in this way. So there are also applications which sometimes are more useful for CFT than vice versa. So, namely, there is a GT relation which relates to the CFT with 4D n equals to 2 star gauge device. And there is also isomorphism CFT relation, which is a little bit similar to this relation to integrable system. I said that to the CFT corresponds to isomorphic deformations of connections of this kind. In D plus sum of AI over Z minus ZI, DZI. And this isomorphic deformations can be described so in some particular cases by Bernoulli equations. And this isomorphic objects also appear in some integrable systems in some probability and so on. We probably will talk about this a little bit at the end if we have time. And basically, I'm going to tell something about QFT in general, do some computations in some particular QFTs like free bosons, free fermions, also look at this Eisen model and to understand why it is related to CFT. And also probably will touch a little bit of all these points. So, are there any questions about the introduction?
Yeah, maybe what could be the mathematical tools or formalism that we will use?
Essentially all the computations, or most of the computations that are done in CFT are computations in the vertex operator algebras. They are not necessarily called this way. People not necessarily use the axioms, but it is essentially this. So maybe I can add it here in the sense that all this is a part of some VOAs. So a VOA is the algebra. Is such algebra which has a Hilbert space. some, or maybe let us just call it is some vector space. The main parts are this. There's a vector space, and there is a map which is called I forgot how people call this, but the map which constructs vertex operators, namely. The map which acts from this vector space to the operators in the vector space. And the picture, and there are some axioms which I don't remember completely, but they can be derived. And the picture for this is the following: that we have some three punctured spheres with boundaries corresponding to the Hilbert space. To this age, and if we take this sequential sphere and put some state here, it turns into the operator acting between h and h. So, and all or most of the computation in CFT are the computations where we multiply several such operators, maybe connect in some other way, and try to find some expansion of this object, or find some equations which are satisfied by it, or find some dimension of space of such such objects. So. So this is what is inside any CFT as a kind of abstract theory. But in particular cases, these CFTs have some underlying description. Like in this case, it is the limit of this discrete statistical model, and it means that we can do some computations in this underlying model. There will be also other examples, for example, free boson theory, where we have underlying description in terms of path integral over the maps from P1, for example, to real numbers instead of this summation. So we will be able to do some computation with in such a formalism, then compare it with the general formalism. So is it some answer or not? Yes. So, are there any other questions? So maybe let us I try to start with some actual computations. So. I want first to show some examples of CFTs. Maybe for the beginning, just one example, and then tell some general theory, so that we can do all these computations independently and check that everything is consistent. So our because we can prove some theorems in CFT, like for example, 3-point correlator always has this form, or that OP of these two operators should have that form. And they will follow from conformal conformal symmetry, and will not know about their particular theory. But on the other side, we can do all the same in some explicit theory with explicitly written Lagrangian, and see that it is consistent. Okay, so our basic example will be the following. It will be the theory with Lagrangian S of phi given by the integral over with the action S of phi, which is given by the integral in dz d phi of z bar d bar phi of z bar. Phi is some real function. So it can be written explicitly. Also, we need to write some coefficient here. Probably it will be 1 over 2 pi. But I'm always forgetting which is the nicest coefficient. And if you write this in usual coordinates, it will be something like 1 over h pi integral on over dx dy and d phi of xy square plus dx plus dy phi of xy squared. So it's like the energy of deformed membrane or the energy of some electric field in two dimensions. So it's a typical classical theory that describes harmonic functions. In a sense, minimal this functional delta S of phi equals to 0 is equivalent to d bar phi equals to 0. So is it is it fine? So, oh, and so if we study classical field theory, then we are interested in solution of this equation with some boundary conditions, probably with some sources. So this is some problem from a classical field theory. But if you go to quantum field theory, it is always a huge jump in dimension of all objects, because here the objects that we study are the following. For example, let us write some operators that depend on this phi. Maybe let's first introduce introduce simpler object. And the first object is this. It is called partition function. And what is written here, what is this integral? It is an integral over all possible functions phi of ZZ bar. Like in this, over the space of all functions. And if we work with um, with functions on some finite set, so some remark. So if phi is from how to denote finite set. So if X is some finite set, to real numbers. Then this notation defy defy will mean product of all x in this set, like the point in this set, d phi of this point. So the function on the set is parameterized by its values at all points of this set, and this integral is the integral over all such values. And if now if phi is from C to R, from the complex plane to R, then we formally write the same, saying that this defy is, maybe symbolically, is a product over all points in C, d phi of p. So this integral is infinite dimensional, kind of continuously infinite dimensional. And when people work with it, when physicists work with it, they usually understand it like that it can be somehow regularized and reduced to this situation. For example, we can approximate, we can describe some function on a plane by its values in some finite subset of all points. So on this plane, write some discrete derivatives instead of continuous derivatives. And when we finish all the computations, or when we realize that this quantity looks universal, we can remove this limit and forget about this structure. Or another possibility is to take some Fourier expansion of this function and truncate some coefficients. So and then again take the limit after the end of computations. And so generally it's not a theorem, but if this theory was nice and physically meaningful, then the way we regularize this integral either does not affect the answer, or does it through some finite number of constants which can be adjusted, and this is called normalization. So if theory was originally finite, then and operators were finite, we will not get any divergences or indefinite quantities. But if no, but theory is still nice, we will get some finite number of parameters which will be more or less clear. But in this situation, in conformal field theory, we will only see such things in the definition of some complicated local operators. It will not affect the theory itself. So, but is this definition more or less clear? Hmm?
So this measure you define from the space of all. I mean, I heard that there is huge conflict.
Which conflict?
I don't know, for dimension one there is this winner measure, I guess, but for dimension two and above, maybe for x finite there is this product you can take, but for C or
I don't know. So the difference between one dimension and two dimension, that in one dimension there is even no place for any possible divergences. And well, we will see it a little bit later. But in dimension one, correlator of the phi behaves linearly. And
so that's why we can make sense of this
measure. Yes, in a sense we can make sense, maybe in some most rigorous way. But in this case, correlator of phi will have a logarithmic behavior, and there will be some quantities which naively are not defined, but can be easily redefined to make a sense of it. So, but actually, two-dimensional case is more complicated than one-dimensional, but I think people still study this rigorously. There is this science about rigorous probabilistic CFT. So they basically represent functions as series in the Fourier or Laurent modes, and say that coefficients of these expansions are independent Gaussian random variables. So I think something can be done rigorously, but I almost don't know this.
Yeah, but
So
that requires some periodicity.
periodicity in what?
I mean, in order to do the Fourier transformation, yes, so for example, in R2 we don't look at it as a function from R2 to R of C.
Oh, but on R2, actually, I don't remember what they are saying, if they work on cylinder or not. Or probably, so they either work on a plane and use a Taylor expansion, or they work on a cylinder and use a Fourier expansion. I don't know. But the situations are more or less equivalent in the sense a cylinder can be mapped to a plane using exponential map, and relation between Fourier and Laurent expansion. So, are there any questions? Okay, so I can go further. Okay, so there was this partition function. So I didn't say what it depends on, but it depends on our particular problem. For example, we can consider this function on a plane, and then it will be just some number or infinite number. We can study it on some manifold, and in this case, it will somehow depend on metric on this manifold. We can add boundary on this and some boundary condition for phi. And in this case, this partition function will turn into the wave functional, and it will be the functional of psi on the boundary. So maybe I can write this example here. So there is a so-called wave functional. Uh, Psi of phi boundary is this integral over d phi with over phi acting on some domain with um, phi on the boundary d equal to this phi boundary. So, if you learn the quantum mechanics, you know that there are wave functions, and if you switch to quantum field theory, you essentially switch to quantum mechanics with the infinite number of degrees of freedom. So our wave functions now become wave functionals. They depend not on some set of coordinates, but on the values of this field on some one-dimensional boundary of a manifold. And by the way, such pictures correspond to computation of operators that can act on a space of such wave functionals. So, but it is something more complicated, and I want to say about a simple object, which is the so-called correlation function. So, which can be so. So there are so-called local operators, or local observables, which I denote by OI. They depend on Z, and they should be somehow constructed from phi. So possible local observables are like a D file, Z bar. We can take some function of phi. For example, we can take e to the I alpha phi of z bar. We can take d phi of z bar squared. So now we are writing this naively, saying that well, we can do anything with the field at some point, but later when we compute something with this quantities, we will see that it's not the actual definition, and the actual definition should contain some regularization. Namely, for example, here we will need to write this field in different points, subtract some singular part, and only after this send these points to 0. In this case, we will need to multiply by some number which goes to 0 or to infinity. And it will be the consequence of this infinite dimensional integral, which defines not like which defines I don't know, not a measure, but something a little bit weaker. So in principle, we can compute all such correlators, but with extra remarks. And this happens in 2D. In 1D, it is simpler. Okay, so and a correlator of such operators is defined in the following way: correlator of O1 of Z1, O n of Zn. By definition, 1 over partition function, integral over d phi, O1 of Z1, On of Zn, e2 minus s of phi, and that's all. So this e2 minus s of phi is a kind of probabilistic measure on this infinite space of functions on two-dimensional plane, or in some cases on some other two-dimensional surface. So is the definition clear? And then I'm going to compute this in our particular conformal field theory with this action. But before this, I want to tell why it is conformal field theory, or namely why CFT. Because if we take phi, if we take some other phi tilde of z and define it as phi of f of z, so it's some other function of z, and compute s of phi tilde as integral over some domain d, well, let us call it d tilde. So d to z means dz dz bar. D phi dz phi tilde of f of z d bar, dz bar phi tilde of f of z. So when I write this, I suppose that conjugate variable is given by the conjugation of this function. So this is homomorphic function. And this notation means that actually phi, so it's a function of both homomorphic and anti-homomorphic variable. And this notation means that it is a function of f of z, f of z bar, like this. Okay, so if I now take this integral and differentiate this explicitly, it will give 1 over 2 pi integral in this domain d tilde. And now we can write it as the integral in f and since now since z was running around this domain d tilde, f will be running over the domain f of d tilde. So it will be the integral over domain f of d tilde df df bar times df phi tilde of f of bar df bar phi tilde of f bar.
So this f is bihomomorphic.
But what is the difference between homomorphic and bihomomorphic? Well, if we don't want to meet some strange problems, then it should be yes, it should be bihomomorphic map from domain d tilde to its image. So there will be this picture that there is domain d. And there is this d tilde, and there will be a domain well, it's some different domain. So it's bihomorphic on its image. And and it's actually an important remark about all these conformal symmetries, because when people say that some theory has conformal symmetry, saying that it is there is some theory on a sphere, they actually mean that it has this local symmetry. Saying that if we consider the action of the theory corresponding to some domain, conformal transformation can map this action to the action of the theory on some other domain. So it is not literally symmetry of this theory on this domain. It is a symmetry which changes the shape of domain. It's important because the number of transformations that preserve the domain is much smaller. It is finite dimensional. So automorphism of this domain are, if it is simply connected, are just SO to R. And if we are on a complex sphere, yes, yes. If we are on a sphere, then this group is a little bit bigger. It is a complex of CP1. It is SO to C. But it's still three-dimensional. Mm, So, so mm, So essential statement about this infinite dimensional conformal symmetry is that there is such symmetry that preserves the action up to the change of boundary. So the difference with non-conformal theory would be precisely this. Because, for example, if I take here not d phi, d bar phi, but take square of this to some stupid operation, of course, but it's doable. If you take here a square of this, this Jacobian of conformal map would appear in the power 2, and it would not hide in the Jacobian of Jacobian coming from measure. So it is essential that we have a dz dz bar, and we have a derivative in dz and derivative in z bar. Hmm? Yeah.
So this is mean different things by symmetry. Some of them may mean, like in this case, that the action is invariant under some transformation. But some people might mean that the equations of motions are invariant under this kind of transformation. Of course, this case implies the other, but can we still call out CFT as CFT if only the equations of motions are invariant but not the action? Or is there such an instance where that happens?
Let me think. Oh, the action should not necessarily be invariant. In principle, it can receive some controlled corrections. For example, it can receive something field independent.
I think
Like
like this first formula, there is the integral of d phi and these local observables and the exponential. Sometimes when you change like this phi by transformation, you add 2 pi I. So the action is changed, but this further action in which the dynamics depend on is not. So maybe that partial. So the action, like the equation of motion need to be invariant, and the action can change up to a term that does not change the partition function.
no, it's
term that only can be
oh, let me think. No, with conformal symmetries, we always have these problems at the boundary because so here the problem is that the boundary changes. But if we try to study infinitesimal transformations, we can neglect this transformation of boundary and just see what happens with the action. And the effect of this deformation of the boundary will produce some boundary terms. In a sense, there will be action plus some term depending on the derivative of this phi and something else the boundary. So the main problem with conformal transformations is of global origin. That there are not so many globally defined conformal transformations, and locally it can of course preserve equations of motion, but globally something can appear. Uh, and let me think about this question more. Mm. No, I think it is always about something on the boundary or the singularities of this transformation. Mm. I don't know.
That our transformations preserves the boundary,
Hmm?
not point-wise, but just as I said.
But this transformations preserve it as a set, not pointwise. If we preserve it pointwise, it will be just trivial transformation. Okay, so there's this conformal symmetry of this action, and mm, also concerning the symmetries, it can also happen that classical theory has conformal symmetry, and equations of motion have conformal symmetry, but at the quantum level it is not conformal. Because the measure can be non-conformally invariant. It is called a scale anomaly, and it appears almost always. So, and there should be some exceptional theories where this anomaly is absent. And it's governed by a so-called beta function, which can be computed. And by the way, the simplest example of such a theory could be like this. Maybe not as simple as this one, but we can write where to write this. So in the action of bosonic string. So the action will be S of x mu, which describes the embedding of this the string in the space. So it depends on all these 26 or as many as you wish components. So z lives on the worldsheet, and the x of z is x mu of z is a coordinate of this worldsheet embedded in the higher dimensional space x1, x2, x3, and so on. So the action is given by almost the same formula. D to Z, it's called Polyakov action. So it will be given by dx g mu nu dx mu d bar x nu plus, so do we need, sorry, I forgot to write g mu nu of what? Oh, sorry, I was lowering this. So let me think. In principle, we can also add B field, which is an anti-symmetric matrix, but but for the beginning, it should be enough. So there is some metric of this n-dimensional space, and we need to substitute here this x of z bar. So it is nonlinear, but on the classical level, this argument still works because we will get we will get just more fields, and they will depend on z. Here we still have a number of like dz bar. Here we still have dz, d in dz bar, d in dz bar. So this action is classically conformally invariant. So equations of motion is satisfied. But if you want this on the quantum level, then a condition that it is conformally invariant means that a Riemann tensor of if you have more field, then this Riemann equations, Einstein equations will have some trivial right hand side, but for simplicity we can write like this. So condition that this string propagating in this curved space-time is conformally invariant gives the Einstein equations. It's kind of the first coefficient in the beta function, and actually it produces some higher corrections in this alpha prime to these equations, and it was one of the motivations why people say that string theory can also include some quantum gravity, although gravity here appears only as a background to the string. So it's some example of this phenomenon. And also, if we don't care about non-trivial backgrounds, it happens that people want to study some sigma model with some nice manifold, for example, with CPN chosen as a target, and it is of course classically conformal invariant because of this argument, and integrable, but at the quantum level, for example, it turns out that integrability breaks. So. Oh, the theory becomes non-conformal for sure because the metric is not flat, but also some other things can be lost due to the quantum phenomena. So, okay, so any other questions? Okay.
So it
Ah,
is another way to recover the Einstein equations using
yes,
the usual way to take this Einstein equation.
but it's a different thing. So it's some kind of independent statement that these equations follow from the action functional. Here we do some computation in this two-dimensional QFT, namely we compute its beta function. And actually, I should write here some corrections, like alpha prime times some, I don't remember precisely what can appear here, like some derivatives of this R, for example, plus something equals to 0. So if you compute more than one loop beta function, we even obtain some corrections to this Einstein equations. So.
And are these corrections kind of compatible with experiments?
Mm, mm, no, no one knows because I think they should be uh, of some non-measurable orders of magnitude. So for sure, people never saw some corrections to this equation in the real life observations, but in principle they study some FFR gravities and make some cosmological predictions, and I think a lot of such theories are not ruled out by modern observational data. So. Hmm? Uh, so condition that central charge is 0 tells us that dimension should be 26, and this is not about the value of the central charge. It is about the even vanishing of trace of energy momentum tensor. It is about vanishing of beta function. So Mm. Uh, but
So the little, like the metric tensor that appears in this Einstein equation is the metric of the 26-dimensional space.
yes, yes.
So it's the same as the big G mu in the
Yes, so this R menu is R menu computed from this G. So it's for the embedding space. Okay, so let us do some computation in this theory. So we know that it is conformal, and so we expect some nice dependence of these correlators on Z and Z bar. And the simplest computation is just a correlator of phi of Z1, phi of Z2. So let us compute phi of Z1, phi of Z2. But uh, to do this is actually is simpler to compute a more general object, namely we can try to compute a so-called generating functional. Which is called z of j, and it is the average of the integral of so over integral in d to z, j of zz bar, phi of zz bar, to well, it's in correlators, so I don't need to write anything else. And uh, why is it nice? Because it encodes phi at any possible points. And now, what happens if we take a variational derivative in phi of z1 and in phi of z2? So who can tell what is the d2 and d phi of z1 and the delta phi of z2 of this exponent? So, who knows, or who can guess what it is? Oh, no, I'm asking just, well, the answer is correct, but I am asking just about this exponent. So, does everyone know how to compute this, or what should be the result? Hmm? Sorry. Well, in principle, both make sense, but of course, I'm interested in this one. Right? So it's basically we can think about this integral as about sum of j times phi over all points in C. Um, uh, Probably multiplied by some area element, but this variational derivatives can be understood as such that they differentiate in the value of j at this particular point without producing any infinitesimal quantities. So it will be just phi of z1, phi of z2 times times this exponential. So if you want, and it is useful because now if you want to compute the correlator of well, which letter am I using for phi? Maybe this phi. If you want to compute the correlator of phi of z1, phi of z2, just need to take this variational derivative. So phi of z1, phi of z2 is equal to delta 2 delta of delta j of z1 delta j of z2 acting on this z of j, and then put j equals to 0. So is it fine? And now let us do this computation. Uh, so So now this partition function, the usual partition function is that of 0, and here we integrate d phi e to minus 1 over 2 pi integral of d phi d bar phi. Mm, mm, one dz bar. And to compute this integral, we want to do the standard trick for Gaussian integrals. Namely, we want to shift integration variable by something j-dependent in order to cancel this term. So we can say that phi is some, well, goes to phi plus some a, Oh. So we see that this shift produces terms of this kind, this one and this one, which can cancel this linear unwanted term and give us some function of a and some integral which is just that of zero, the integral without source. So this j is called the source. I want to integrate some of these terms by parts to be able to combine them. So it is like this. Oh, plus actually both of these terms produce the same answer, so it will be 2 over 2 pi. So it will be two similar terms. Mm. Then let us write this term explicitly, plus phi j. Mm. This term and the last one. And now, if you choose this a in such a way that these two terms cancel, we will immediately compute this integral in phi, which will give just that of 0, and compute the value of these two terms. If we want them to cancel, so we want this to be 0. So we say that d bar of a equals to minus pi j. Or in other words, we can say that it is a Laplace operator and we can invert it. We can say that a is minus pi d bar inverse, or maybe, well, 1 over d bar a. So substitute it here. And so this integral can be immediately computed after this. So it disappears. It cancels all of this. And we get integral and we get just e to 1 over 2 pi. I'll try it better. So it is d bar 1 over d bar j multiplied by 1 over d bar j. and also multiplied by pi squared. In the first term. The second term, which is minus pi j 1 over d bar j. So the final answer is e to minus pi over 2. And I also forgot to write the integral in d to z. Uh, so there is some expression, but we need to expand it further. And who knows what is the inverse operator to the Laplace operator? So how does this? Mm-hmm. So this 1 over d bar j means it means some integral operator with explicitly known kernel. So it is e to minus 1 over minus p over 2 minus pi over 2 p over d to z d to w j of z bar, some green function of z z bar.
Sorry. Could you say again what you mean by 1 over the bar?
It's a solution of this equation. So it is yes, it is the operator acting on a and so the right hand side contains j. So it's green function of this operator. So so here's the answer for the generator functional. It's this quadratic exponent, and it is the general phenomenon. Then, if the action is quadratic, then the generator function is quadratic, and this is what is called free field theory. So if you want to compute this correlator now, you can just express it in terms of this green function. And because there will be some point where so d2 over j of z1 j of z2 will look for j at point z1, for example, this j of point z1 and this j of point z2, or vice versa. But this kernel is symmetric, so it does not matter. And this two terms will add up. So the answer will be minus pi green function of the 1, z2. O of the j for j equals to 0. How much? And what can I write? Oh, build it. So, and who knows the green function of two-dimensional class operators? Namely, so if you have such equation, how to write its solution? Hmm? Well, we can do this. So one possible way is to say that it is if we if you go to momentum space, maybe it is better to use mm, usual coordinates like x and y. Mm, so this dd bar is 1/4 dx squared plus dy squared. So then green function of r will be integral d to k over 2 pi squared e to the I chi ik r or 1/4. So in principle, this integral is divergent, but it's not very big problem because we can regularize it. So what is the overall prefactor? Overall prefactor is 1/pi squared, and let us raise this k squared to the numerator by integrating in lambda minus lambda k squared. Maybe it's better to introduce some regularization at the very beginning. So in principle this integral is divergent at small case. So better put here some m squared and then remove it minus lambda m. So then let's integrate on this in k. Will be so. Like this, and what is together here the full squared, full square. So it's the integral like this, and mm, uh, there is some no. So in principle, this can already be computed, and it is some I forgot precise formula, but it is k0 of m times r. So it's a modified Bessel function, mm, mm, and we can first compute it and then study the asymptotics of this function. But it's actually better to study it without any special functions. So we can mm, mm, let me think. Let me say what is the answer here. Uh, so here the answer is something like a logarithm of m times r. So this integral is logarithmically and divergent in the limit m goes to 0. But if we take the difference of this integral for different values of r, well, for some corrections, then this mass dependence disappears. Um, and let us try to capture this phenomenon here. So if we naively remove this regulator m and write it as is, we will have mm, some divergence at lambda going to infinity. Because when lambda goes to 0, this exponent goes to 0, and everything is fine. But actually, it is better to change lambda to lambda inverse to have this divergence at 0. So this integral equals to 1 over pi integral d lambda over lambda 0 to infinity e to minus so it is regulator at 0. And let us now consider the difference of two integrals. Oh, g of r1 minus g of r2. It will be the integral 1 over pi integral from 0 to infinity d lambda over lambda r1 minus the same for r2. And we see that now this difference go to 0 when lambda goes to 0. So the integral is now convergent, and we don't need this massive regulator. So we can send m to 0 and write it like this. So it vanishes when r2 equals to r1, and equals to something otherwise. And so in principle it's called Fournier formula. So we could have arbitrary function of some r1 times lambda and r2 times lambda. But in this case we can do even simpler. We can just differentiate in r1 and see that it is it's now computable. So it will be minus r1 over pi integral d lambda from 0 to infinity and this integral can be computed. It is just 4 over r1 squared. So in total it is minus 4 over pi r1. No, sorry. Why did I write it like this? So it should be divided by 2 pi. So g of r1 is with some coefficient like minus 2 over pi. Where? But no, it was double integral. but there are two Gaussian integrals. And this integral is just integral of exponent lambda. So it will be minus 2 over pi logarithm of r1. And here we need to remember about the fact that original integral for m equals to 0 was divergent. It is one of those divergences, but it is called infrared divergence because it appears on the big distances. So so there is some parameter in this gain function which is not fixed by the equation, but which will appear in the answer. Because correlator of phi and phi is just this gain function. So it will be visible. And this interpretation of this parameter is something like the size of the system. Because, for example, we can write this grain function for the disk, not for the plane, and there will be no this problem. And let us actually see it. By the way, this formula can be also written in the following way. It can be written as minus 2 over pi logarithm of minus 1 over pi, logarithm of z over r plus logarithm of z bar over r. So it's the first appearance of this phenomenon that if you work with CFT, there is usually this separation between homomorphic functions and anti-homomorphic functions. So, so if you finally try to write the answer for this correlator, where did I write it? No, so this is the correlator of phi z1, phi of z2. So taking into account all these minuses and so on, pi's we get logarithm of z over r plus let us logarithm of z1 minus z2 over r plus logarithm of z1 bar minus z2 bar over r. So it's the answer. And if you want to see some conformal invariance at this level, we need to go a little bit further. Namely, we need to consider the correlator of fields d phi. So I would like to consider dz1 d phi plus times dz2 d phi. So we need to differentiate this logarithm. And it will equal to 1 over z1 minus z2 squared. Actually, I'm afraid that I missed some sign somewhere because in principle Mm, mm. In principle, there should be negative sign in this formula. Mm, but maybe I cannot reconstruct it now. But we'll probably fix it later. Yes, so and there is also dz1, dz2. Uh, so we obtained some one form which lives on a product of CP1 and CP1. So it is denoted something like omega 1 on CP1, and this boxed tensor product. So there is such a B differential that has second order pole at diagonal, and its a remarkable property is that it is invariant under under fractional linear transformations of this CP1s. Namely, let us check the following. And it is called Bergman kernel. So, uh, so if you want to check this, it's enough to check the three transformations that generate this group. One is z to lambda z. Well, actually, it's kind of second, but we also have z to z plus a, and Western transformation is inversion, z to 1 over z. So is it obvious why it is invariant under the first two transformations? So lambda squared coming from here and lambda squared coming from there. Here it's even simpler. Each z is shifted by a, and difference is not shifted. And the only tricky thing is this last transformation. So here we need to write d z1 over z1 squared, d z2 over z2 squared over 1 over z1 squared minus 1 over z2 squared. Oh, sorry, 1 over z1 minus 1 over z2 squared. And it's also not hard to see that it is like z2 minus z1 squared. So this is cancelled by this. So it's also invariant. So as expected, such object is invariant of the global conformal transformations. And but this is something, and we see that it is not very nice. It has some scale parameter, but in general, if we think that logarithm is almost constant, we can say that its dimension is 0. So, mm. So such dependence of a correlator is the typical dependence in CFT, because we don't have yes, dimensional parameters rather than this R, which appeared only in one correlator. So we can only construct some powers of this, and it's a restrictive condition. So. So then I will explain that we could find this formula from the general theory in several different ways. So are there any questions?
Yes.
Mhm.
So before this lecture, I wasn't pretty familiar with any of what we've done so far. So it was a bit hard for me to discern what is classical theory, let's say, and what is should be conformal theory. So what I wanted to ask is what the specifically in this is should be conformal theory. So what techniques would I learn to use specifically this kind of course?
To deconformal field theory is, first of all, it is a quantum field theory that has a conformal symmetry. Then it can be studied from two different, or maybe even three different point of views. We can develop some general theory which will explain how to compute objects like this without going into details how this theory is realized. So here we use explicit representation that this correlator of phi's equals to this integral in phi exponent in integral phi, so phi. But we can use conformal symmetry to derive some so-called conformal word identities, which should be satisfied by these correlators. And then we can forget about the existence of this representation. It turns out that in 2D conformal field theory, this conformal word identities will be sufficient to fix correlation functions well to some extent, because in principle we need some way to distinguish different theories, and sometimes we can. So usually we can think about conformal field theory as just about some machine which gives you some expressions for the correlators. that should satisfy this conformal order identities. And we can study it in this abstract way using using vertex separator algebras or some other techniques. But if you want to say what concrete theory it is, we need to remember such kind of representation. And I'm showing this example first to have some examples of the correlators computed explicitly, and second to become a little bit familiar with this path integral technique, because we needed to find conformal word identities. So once we derive them, we can forget about the origin. And even more, one theory can have different representations in terms of path integral in different variables. For example, there can be bosonic and fermionic description at the same time. Or in the Ising model, there is this statistical mechanical description and fermionic description. So it's not a unique representation. The unique is this set of correlators. So we need to understand this, and then we can mostly work just with correlators. So is it kind of answer? It's an answer to a different question. Mm. So, but in general, if you think about conformal, if you think about quantum field theory, we can think about it as about some machine that computes correlators, and sometimes this representation is not even known, and people just take this conformal word identities or some other identities in different theories, for example, in topological theories, and the axioms and the right, like axioms for CFT or axioms for topological field theory. So, but all of them can be derived if we suppose that we know some representation in terms of path integral. So it's kind of motivation for these axioms. So, are there any other questions? Okay. So, thanks for your attention. See you on Monday.
To the audience.